Hi there, welcome to this Elkchemist chemistry video looking at mole to mass conversions and vice versa. So when you think of the term mole, you probably think of maybe a cute little cartoon character like this. You might think of the actual mammal itself, like this cute little chap here. You may even think of the nightmare fuel of the star-nosed mole, like this abomination here. But actually for a chemist, none of these images come to mind. Actually, this number appears in the mind of a chemist. And I want to explain exactly what this number means and how we utilize it in the real world. So what exactly is a mole? Well, in layman's terms, it's just a quantity used by chemists to measure out certain amounts of substance. Here's a simple analogy. If I sent you to the shops to buy me some eggs, you wouldn't just give me a random assortment of eggs of various different number. You'd come back with a very set, quantized number. You'd probably come back with something a bit like this. This is half a dozen eggs in a little box, carefully unbranded. It's a set value that we all understand, we all can conceptualize, and we can all imagine in our minds. That's exactly what a mole is to a chemist. It's a set quantity of chemical substance. Unfortunately, atoms and molecules are infinitesimally small. So even small amounts of substance will contain truly vast numbers of atoms and molecules. So the mole is defined as a quantity used by chemists to measure and compare the quantities of different substance. 1 mole of a substance will contain 6.023 times 10 to the 23 atoms or molecules, a truly gargantuan number, very hard for humans to comprehend. This number is also known as Avogadro's number. Fortunately, the applications of this number in the real world in terms of grams and masses is much simpler for us to handle. At this point I want to introduce the idea of molar masses. It turns out that mole values are intrinsically and indelibly linked to the relative masses found within the periodic table. So the real-world mass of 1 mole of a substance is equivalent to its relative mass expressed in grams in the real world. So effectively, 1 mole of a substance is its relative mass in grams. Let's think about that right now. So if you look at the periodic table and find the relative mass or mass number of carbon, you'll find that it is 12. And therefore, according to this definition, 1 mole of carbon atoms would possess a mass of 12 grams. And if you measure 1 mole of carbon, it does possess a mass of 12 grams. So these are real world values. So now I have a question for you. What would be the mass of 2 moles of carbon? Have you got it? Absolutely right. It'd be 2 times 12 grams. In other words, it'd be 24 grams. 2 times the mass of 1 mole of carbon. What about 3 moles of carbon? How much mass would that have? Well, it stands to reason it would be 3 times the mass of 1 mole. In other words, 3 times 12 grams. 36 grams. How about half a mole of carbon? Well, if you multiply 12 by a half, or divide by 2, you would get 6 grams. The mass of half a mole of carbon, if carbon's molar mass is 12 grams per mole. So hopefully by now we're starting to demystify the mole, make it a little bit less scary. I'm now going to show you how you can use a formula triangle, just like you use in physics, to solve molar calculations. So let me explain where this triangle comes from. We now know that effectively 1 mole of a substance is equivalent to its relative mass expressed in grams. So if we make this n term, this mole's value 1 times the relative mass of the substance will give us its mass in grams. So any number larger than 1 would have the same effect. We multiply the number by the relative mass to give us the actual real world grams value for that substance. And that's this rearrangement going on here. Now, once we arrange that information into a formula triangle, we can manipulate that formula triangle to work out any of the 3 values we like, simply by covering the one we're looking for. For example, if I want to know number of moles, I cover the n on the triangle, showing me the function would be mass in grams divided by relative mass to give me moles. In other words, this arrangement here. On the other hand, if I want to work out mass, I cover mass with my hand, showing me the function would be number of moles times relative mass, which is the second rearrangement shown here. And finally, if I want to work out relative mass for a sample, I cover relative mass on my hand, showing me the function would be mass divided by number of moles, which is shown by the third rearrangement here. So we can work out any of the values as long as we know the other 2. Now, chemists aren't quite as generous as physicists, so you have to memorize this formula triangle. So don't forget, guys, memorize the triangle. Okay, ladies and gents, just before I carry on to the next section where I go through some word examples, don't forget, if you find the video useful, please think about giving it a like. You could subscribe to the channel. You could even ring the bell to get notified about latest content. I try and put videos on a weekly basis. You could even share this content with friends studying chemistry to help them along as well. Your support is hugely appreciated and helps motivate me to make videos on that weekly basis and to spread the learning of chemistry as widely as possible. Without further ado, let's carry on with this video. Let's have a look at this first word example. I'm going to show you how to put down perfect working every time. So we've been asked how many moles are there in 15 grams of water if water has the formula H2O. Well, the first thing I do in the margin is write down that formula triangle, okay, NMR. I then cover the thing I'm looking for. We're looking for moles, that's the N. So I realise that moles is calculated by doing mass divided by relative mass. I then immediately write down that rearrangement as my first step in the calculation. At this point, I then enter the values for the mass and the relative mass. So 15 grams from the question, and the relative mass of water is 1 times 2 for the 2 hydrogens and 16 for the oxygen, taking the mass numbers from the periodic table. That working is shown here. Effectively, that's 15 grams divided by 18 for the relative mass of water, giving me a number of moles as 0.833 to 3 significant figures, which is the standard level of precision you should leave your answers to in all chemistry papers. Now let's have a go at worked example number 2. In this question, we're asked to work out how many moles there are in 20.4 grams of magnesium. And magnesium has a formula Mg and is a metallic structure. Again, good habit, I put that formula triangle in the margin to work with. I then realise that we're trying to work out moles, so I cover the N moles symbol with my finger, and the function we need to do is mass divided by relative mass. Immediately as my first step, I write down that rearrangement, and then I put in the numbers from the question. That's 20.4 grams of the mass. I look up the relative mass of magnesium from the periodic table, which is 24. So 20.4 divided by 24 gives us a number of moles as 0.85 or 0.850 to 3 significant figures. Let's see a question with a slightly different tack. This time we're being asked to calculate mass. What would the mass be if we had 10 moles of ammonia, and ammonia has the formula NH3? Again, write that formula triangle in the margin, but this time we're trying to find the mass. So I cover M with my finger, realising the function will be moles times relative mass this time. So, first thing I do is record that rearrangement. Mass equals moles times relative mass. I then plug in the numbers I've got. 10 moles, and I have to work out the relative mass of ammonia. Well, nitrogen has a relative mass of, or mass number 14 for the periodic table. Hydrogen is 1, there are 3 of them, that's 1 times 3. 14 plus 1 times 3 is 17. So 10 times 17 tells me that the actual mass in the real world of 10 moles of ammonia would be 170 grams. Our final question is also a mass question. What will be the mass of 100 moles of ammonium phosphate? Ammonium phosphate has the formula NH43PO4 and is a component of fertilizers. So again, our good habit, we would write the formula triangle in the margin, NMR. We then think about what we're trying to figure out, which is mass. We'd cover mass with our finger or thumb, showing us the function is moles times relative mass. We'd write that down first of all, mass equals moles times relative mass. We'd then plug in the numbers. N is going to be 100 and R is the relative mass of the whole formula of ammonium phosphate. That's worked out here. Nitrogen 14, hydrogen 1. There are 4 hydrogens in NH4, so it's 14 plus 1 times 4. But that is in brackets with a 3 on the outside, so multiply that entire formula unit by 3. Add to that the 31 of the phosphorus, and 16 times 4 for the 4 oxygens. The total relative mass of the entire molecule is 149. 100 times 149 is 14,900 grams, or effectively 14.9 kilograms. And there we have it, folks. That's the end of the video. I really hope that's helped to simplify and in some respects demystify the terrifying prospect that is moles, and you'll be able to tackle those sort of questions much more easily in the future. And just suffice me to say, thank you so much for listening. I really enjoyed talking to you, and I look forward to talking to you in the next Elkchemist video. Take care. Bye now.